All right, guys, we're going to talk about 6.5 today, linear optimization. I can use linear programming to solve applications, was one of our lesson goals. Another one is to be able to recognize situations where there are no or more than one solution of a linear program application. All right, now where do we use optimization? Well, easy real-world examples there are in the world of business because businesses exist to make money, right? Not just any kind of money, they exist to make profit. All right, now in their search for profit, they find that they run into constraints, right? Budget, staffing, scheduling, policies, politics. So those are things that can create or increase businesses' costs, which can limit or decrease their profits, right? So that idea of constraints, it's not just something that businesses use and you can't apply it anywhere else. We see that in optimization problems and linear programming. All right, it's one of our vocab terms for this unit. So optimization is pretty much what you'd think it is. It's the process of finding a max or min value for a specific quantity. And in this lesson, since we're going to be working with optimization and linear functions, so we're going to be talking about something called linear programming. Now, in linear programming, we have an objective function, which will be something that we're optimizing. Right, so it looks kind of weird right now. F of xy is equal to ax plus by plus c. You're like, wow, I know ax squared plus bx plus c from quadratics. Is it a quadratic, Mr. Wine? Did you make a typo? No, it's ax plus by plus c. And the xy, we'll talk about that here in just a little bit because I know you're also used to f of x. So the f of xy is something that can throw you off. Then we have, just like businesses, right? We have these things, these linear inequalities that act as constraints. So those are things that can limit our values. So that can limit our ability to optimize or maximize a value in a given problem. And then this portion, feasible solutions. So those are just XY points given our objective function and our constraints that allow us to say, yes, this maximizes or this minimizes or, what have you, depending on what the problem asks us to solve for. So how do we find a max value? Well, we use something called vertex theorem or the fundamental theorem of linear programming. So vertex theorem or the fundamental theorem of linear programming tells us that if we want to look for this optimal value, so we're going to graph our constraints, and that's going to create for us a shape that has vertices, right? So we're going to go to each one of those vertices and test those vertices, and our optimal value is going to occur at one of these vertices in our feasible set. All right, so here we just have a picture of kind of what that looks like. So you have a bunch of different equations, and when you put those together, let me be a little precise in my language, inequalities, right? So we had these inequalities and we used those constraints, and we came up with an image that has 4 vertices. Okay, cool, but what about an actual problem? So let's take a look at an actual problem. We have 2 samples to work right now. I'm just going to go ahead and clone this page. So very straightforward, right? We just want to graph the region corresponding to our system of constraints. We want to find the coordinates of that region's vertices. Then we want to evaluate the objective function at each vertex to see which values, if any, are going to maximize or minimize the function. All right, so the first one we're looking at is this, f of xy equals 2x plus 5y. So the xy means, right, if we have a vertex, right, the vertex is not 2. The vertex occurs at 2, 5. So that's why we have that f of xy, because if we're looking at a point, any point is going to have an x and a y coordinate. So that's why it's f of xy, because we need the x and the y value of that coordinate to plug that point back into this objective function. So if we want to be able to graph our constraints, so that's what these things are right here. These are our constraints. If you want to try to put these inequalities in what resembles the inequality version of y equals mx plus b4, right? So here, that's going to be y is greater than or equal to, so negative 3 minus x. Here, 3 goes into 6, 3 goes into 3, and 3 goes into 24. So I'm going to factor a 3 out of everything, right? So that's going to give me 2x plus y is less than or equal to 8. So that actually tells us that y is less than or equal to 8 minus 2x. So 1, 2, 3, 4 constraints. What does that look like when we graph it? Come on, let me extend the page. There we go. All right, so 8 minus 2x. Okay, so 8 minus 2x. So we're up here at 8 on the y-axis, right? Because y equals mx plus b. So that'll be our y-intercept, right? So then our slope would be negative 2. So we're just going to follow this down right out here till we get to 4, 0. All right, now we need everything that's less than or equal to that. So less than or equal. So I'm just going to shade. So that's all these yellow lines are right here, just represents my shading. So now I'm going to come back here and we go to negative 3 minus x. So negative 3 is our y-intercept, and then negative x means our slope is negative, right? So change in y over change in x, rise over run. So we're rising, in air quotes, negative 1 unit for every 1 unit we're running to the right along the x-axis. So that one is going to have slightly less steep slope. So they're going to meet somewhere over here, right? So that's the y less than or equal to negative 3 minus x. There's that greater than or equal to. So y is greater than or equal to, and this one is y is less than or equal to 8 minus 2x. Okay, so what are we going to be shading here? So we're looking at greater than, so I'm going to do yellow, but I'm going to do the yellow at an angle. Okay, so yellow, come on, yellow at an angle. Now what about the y is greater than or equal to 0, x is greater than or equal to 0? Well, a lot of times, especially when we end up talking about business stuff, right, you're talking about profits, well, you can't have negative money. You can make 0. That's it. Nobody wants to make 0. You're not going to earn negative money. You can earn anything from 0 to whatever. All right. So if we're looking to maximize profit somewhere, to optimize something that involves money, the greater than or equal to 0 on the x and y axis, that's going to be something that's key for us moving forward. So please pay attention to that and be able to reason through that and these problems. Now, that being said, right, so x and y. So this would be y is greater than or equal to 0, right, because we're going up the y-axis. Then for x is greater than or equal to 0, it can be shading out here. Now, if you notice, all of these things meet up in this little area right here. All of our shadings meet up right here. Now, that's a triangle, which means we have 1, 2, 3 vertices. Now, what are the coordinates of those vertices? So we have y is less than or equal to 8 minus 2x. So our y-intercept is up here at 0, 8. And that intersects, right, with our line x is greater than or equal to 0. So 0, 8 is 1. Then we have the x and y both greater than or equal to 0. So that gives us this right here. That gives us the origin. And in this right here is where y is less than or equal to 8 minus 2x intersects with the x-axis, and that is a place where x has a value of 4. Right, so to figure out that, we would just say, okay, so x has to be greater than or equal to 0, so 0 is equal to the 8 minus 2x, 2x equals 8, x equals 4. All right, that's how we get that. Now, we take those 3 points. Now, I hope you'll look at this and consider 0, 0, 0, 8, 4, 0, and consider that when we say f of x comma y, that's really talking about the fact that each one of these pairs, each one of these vertices, has an x coordinate and y coordinate. All right, so that's what we're dealing with here. And our objective function is 2x plus 5y, so let's plug it in, right? 2 times 0 plus 5 times 0. 2 times 0 plus 5 times 8. 2 times 4 plus 5 times 0. So 0 plus 0 is 0. 0 plus 40 is 40. 8 plus 0 is 8. So 0, 0 is our min. 0, 8 is our max. There we go, guys, and it is just that simple. So we do the same thing over here for our next problem. So 5x minus 6y is our objective function, and this one's nice and neat, these constraints, because we don't have to readjust those. We can just sit there and graph all of them. So that is fantastic. So I'm just going to come over here. All right, so negative 3x minus 12. Once we come down here to negative 12 and negative 3x, so we kind of have a sort of a steep slope right there. So that's y is greater than or equal to negative 3x minus 12. Y is less than or equal to 6. So we just have a horizontal line extending out to infinity and negative infinity from 6. So right there, so that's a line y equals 6, right? So we go toward infinity along the x-axis, toward negative infinity right there, and that shows us that y is less than or equal to 6. And you say, well, what do you mean, Mr. Y? You just drew a line. How do we know that it's because we're shading down here to prove it? We want y is less than or equal to 6. We also want that y is greater than or equal to negative 3x minus 12. And we want that y is greater than or equal to 2x minus 2. So minus 2 is going to be up here, and 2x, so our slope is going to be positive. So we're coming up right through here. And we want greater than or equal to, so we want above. So where is the only place on here that you see the shading match up for all of our constraints? That's right here, right? So this is our feasible set of values right here. And once again, it looks like we have a triangle, so we're going to have 3 vertices to check out. Now, how do we figure this out? As the vertices are actually pretty easy to get on this other one because we had, y-intercept, intersection of this and a y-intercept, and then we had an x-intercept. So over here on the second one, we have to do a little bit more legwork on it, but it's not impossible. So the first thing is, and I'm going to go ahead and come over here and erase this so we can do the first thing. Okay. So the first thing is this line where y equals 6, because we wanted everything to be less than or equal to 6. So we have negative 3x minus 12. Well, that actually intersects with the line where y is equal to 6. So negative 3x, when we add 12 to both sides, negative 3x equals 18. X equals negative 6. So one of our vertices is negative 6, 6, negative 6, 6. All right, this vertex right here is where 2x minus 2 meets 6. So 2x equals 8, because we're adding 2 to both sides. So x equals 4. So that means this vertex is 4, 6. And this one down here is where negative 3x minus 12 is equal to 2x minus 2. So I'm going to add 2 to both sides. I'm also simultaneously going to add 3x. So we get 5x equals negative 10. So x equals negative 2. Substitute that back into one of the originals. So 2 times negative 2, negative 4 minus 2, negative 6. All right, so we have our 3 values. Right, so we have negative 6, 6, 4, 6, right, 4, 6, and then we had negative 2, negative 6. And we want to put those into, right, because that's our f of xy, right, because we're putting the x and the y coordinate of that vertex into this objective function, 5x minus 6y. So you say, well, we had the ax plus by plus c. Where's the c? You're not always going to have the c. Don't worry about that. Or that's just giving you the most general form. You're not always going to have it. So you plug that in. So we have 5 times negative 6 minus 6 times 6. 5 times 4 minus 6 times 6. 5 times negative 2 minus 6 times negative 6. So negative 30 minus 36. 20 minus 36. Negative 10 minus negative 36. So minus and negative means plus positive, so that becomes 36 minus 10 or 26. This is negative 66, and this is negative 16. So negative 6, 6. So this becomes our min. And then negative 2, negative 6 is our max. All right, that's not so bad, is it? This one, a little bit of a bear, possibly. A lumber mill can produce up to 600 units of product each week. So think about like 5th through 8th grade math and then some algebra 1, up to. So at most versus at least. So up to 600 means we can't go past 600. Right? We can go up to 600, but we can't go past it. So that means at most. So we're looking at a less than or equal to. The mill must produce at least 150 units of lumber. So X has to be greater than or equal to 150, because I'm going to say let lumber. So let X equal lumber, let Y equal plywood. At least 225 units of plywood, so greater than or equal to 225 is what Y is going to be, right there. Because once again, we have this idea of at most versus at least. And then profit of $30 for each unit of lumber and $45 for plywood. Okay, so what are we doing with that? Write an objective function and a list of, oh, you know what that's going to be? So these things are going to be our constraints. And this is going to be our objective function because we want to maximize our profits. So we're talking dollars and cents, $30 and the 45 cents. Now, something nice about that 150 net 225 is that it's money, right? So we know if they didn't say anything about the 150 and 225, we know that we can't go more negative than zero anyway, because once again, we're talking about money. All right, so it should make sense that it's going to have to be positive. Now we said X plus Y is less than or equal to 600. So Y is less than or equal to 600 minus X. Boom, right there. So that's X plus Y is less than or equal to 600. So X has to be greater than or equal to 150, and Y has to be greater than or equal to 225. So I have my lines. Now what about the shading? So less than or equal to 600, I'm going to shade underneath there. Greater than or equal to 150, and greater than or equal to 225. So where do all of those things meet up for a feasible set of values? Right here. Okay, so what does it mean for us? Well, it's a triangle, so we have 1, 2, 3 vertices. Oh my gosh, what are those things going to be? Well, one of them, because we have the lines x equals 150 and y equals 225 meeting up, so one of those will be 150, 225. Okay. Another point out here, so y is 225, and that intersects our graph of y equals 600 minus x. So x, 600 minus 225, so x equals 375. So we have 375, 225. And then our third point is where x equals 150. So all right, so in that case, so if x is greater than or equal to 150, x plus y is less than or equal to 600. So x less than or equal to 600 minus y. So we have 150 is equal to 600 minus y. So y is equal to 600 minus 150, 450. But why can't I go ahead and put that in for the x? Why can't I have 450 for x and 150 for y? Well, that's where we have to use some common sense and some reason here, because x is equal to 150. So that means you have to go back up and rearrange this equation so that we can have the x of 150 equal to our x and whatever over here, right? So by the transitive property, if a is equal to b, right, and a is equal to some c over here, then b is equal to c. So that's why you're not messing with x and y and saying that it's, saying that that's 450x and 150y, because x is what is greater than or equal to 150. So our third point is 150, 450. Now let's take those and let's do our f of xy, right? So we have 30x plus 45y. So that's going to give us our 3 points, right? So we had, so 150, 225. So 150, 225, 150, 450. And then we have 375, 225. 375, 225. And we want to maximize this. All right, so if we're looking to maximize this, it means we're only going to have one feasible solution here. So they get my calculator up. So 150 times 30. So come on up here. So it really doesn't like when I try to move and then write pretty close to each other. So 30 times 150, so 4,500 plus, okay, so 45 times 225 plus 10,125, so 14,625. Then we have 45 times 450, so we have 20,250. So that is $24,750. All right, and then 375, 225. So we know that the 225 gives us $10,125. So what's 30 times 375? 11,250. When we sum these together, we get what, 21,375. So 21,375. So 24,750 is greater than 21,375 and 14,625. So what's going to maximize this? 150 units of lumber and 450 units of plywood. That's what's going to maximize. Come on down. Come on down. There we go. So 150 units of lumber, 450 units of plywood. That's what is going to maximize our profit. All right. Now what about this? No or optimal solutions. All right, if you solve the objective function for y, you'll get the equation related to the objective function, okay. If this is coincident with one side of the region, then f is going to have multiple optimal solutions. If the region is unbounded, i.e. it's not a polygon, then f may have no min or max value. So what does that mean for us right here? So as we see in this picture, so our objective function, right, has a slope over here, and that slope is equal to the slope of our constraint on the line AB, which means every single point on this line from A to B is going to be an optimal solution to this problem. So everything here from A to B is going to be an optimal solution right here. So what's going to be infeasible, come over to the next picture over here. So A, we have a unique solution represented by a corner point And then we have alternate solutions represented by points on one of the constraint lines. All right, so in A, we have a unique solution, right? So 1, 2, 3, 4. Yes, we have 5 vertices. All right. Let's see, B has no feasible solution because what we want to do is we want to shade here, here, and here. So we don't have a region that matches up with all of the constraints. And then C, we're not going to have a solution because it's unbounded. So we don't have a bound out here in C. So how does that translate to some sample problems? Well, let's take a look at these. 4x plus 3y is greater than or equal to 12. All right, y is less than or equal to 3, greater than or equal to 0, x is greater than or equal to 0, or less than or equal to 4. Oof, a lot of constraints. That's okay. That's okay. Let's work through those. Let's take a look at this. So 4x plus 3y is greater than or equal to 12. So 3y is greater than or equal to 12 minus 4x. So y is greater than or equal to 4 minus 4/3 x. Okay. Let's see here. So 4 minus 4/3. So we need, I'm actually going to clone this page right now. And when I clone it, I'm going to clear the ink from the page. There we go. All right. So we come here. Y is greater than or equal to 0. So greater than or equal to 0. So we're going to come up this way. Less than or equal to 3. So less than or equal to 3. Okay. X is less than or equal to 4, but greater than or equal to 0. So greater than or equal to 0, less than or equal to 4. So we're looking at greater than or equal to 0, less than or equal to 4. So right now we have this little boxed in region right here. So let's see what happens when we add the y is greater than or equal to 4 minus 4/3 x. So we come up here to 4. So down 4 over 3. So okay, so we have this region right here. Okay. So we have a lot of things to consider right here. So this is our, so I'm going to say right here, y equals 4 minus 4/3 x. All right, so what are our vertices? Well, right here we have 0, 3, 0, 0. Then right here we have where 3 meets up with 4 minus 4/3 x. So 3 equals 4 minus 4/3 x. So 4/3 x equals 1, because I'm going to add 4/3 x on both sides, take away my 3. And then when you divide by fraction, I'm going to clean this up right here. So you divide by a fraction, keep change flip, you multiply by the reciprocal, right? So x equals 3/4. So we have 3/4 and 3. So that's 3 of these. Our fourth thing right here. Okay, so this is one where we have, looks like x is equal to 0, and we have 4 minus, so 4 minus 4/3 x. So x is 0 and y is equal to 0 right there. So let's see here. So what are we going to do over this way? So trying to find out what x is right here when y is equal to 0 on the x-axis. So 4/3 x equals 4. Divide by 4/3. Boom. So x equals 3. So we're going to have 3, 0 right there. All right, so 1, 2, 3, 4 points, and let's see what's going to happen right here. So we have 0, 3, we substitute that into 3x plus 3y. So we have 0, 3, 0, 0, 3, 0, and 3/4, 3. Okay, and we have 3x plus 3y. All right, so 3x plus 3y, 9 plus 0 is 9. 3x plus 3y, 0 plus 0 is 0. 3x plus 3y, so 9/4 plus 9. So 9/4 is really 2 1/4. So that is 11 1/4. And then we have 3 times 3 plus 3 times y, 9 right there. So what do we notice about this problem? Well, you should. Okay, you know what I just realized right here? Funnily enough, I'm going to delete this right now. I shaded the wrong direction, didn't I? As I'm looking at this, it's y is greater than this, and what I do, I shade it underneath. So actually, so it should be this region right here. So is that a huge course correction to make? No, just means that I need to have a couple of cups of coffee before I start doing this stuff, because I had it right there in front of me. So it's a lesson to all of us that, you know, you're you're not done until you go back to check and make sure that your answer makes sense. So I'm looking at this, I'm like, wait a minute, what's going on? So it's just the other side. And that's actually pretty easy to get because we already have one of those, right? So we did that. So we have our 3/4 3 doesn't change. So over here at this point, so we have an x value of 4, a y value of 3. Then we said, what, over this way? So we said, x was 3. So we had our 3, 0, and right out here we have 4, 0 as well. So we had all of our, we had all of our constraints. So we have 1, 2, 3, 4 points. So 3x plus 3y. So there's nothing wrong with that. It happens sometimes. So just make sure you're awake and working on the stuff. So I'm leaving that in there because, you know, sometimes you want to go in and be like, oh no, everything's always perfect. Well, no, it's not always perfect. Right? I'm finishing my first cup of coffee. My mind is, you know, not all there without finishing that first cup of coffee. So I want to leave that error in there because that's important for you to see. It doesn't mean you can't do the math. It doesn't mean you have to start all over. You say, oh yeah, okay, just a little bit of course correction. So 3/4 3, 3, 0, 4, 0, and 4, 3. All right. So over here, so 3 times 3/4. So we have 9/4 plus 9. 3 times 3, so 9 plus 0. 4 times 3. Right, so you didn't see this before, so I'm gonna show this. Plus 0 times 3, because we saw these on the other side. So that's 12 plus 0, that's 12. This is 11.25, this is 9. And this is going to be 3 times 4 plus 3 times 3. So that's going to be 12 plus 9, that's going to be 21. And what in the world are we doing on this problem now that we have all of these numbers? We want to find the max and min subject to these given constraints. All right, well, 9 is certainly the smallest value I see. So where min occurs at 3, 0. And our max, I don't know about you, but 21 to me looks bigger than 12 and 11.25. So our max occurs at 4, 3. Bing, bang, boom. All right, so we go into this next one right here. Oh, check this out. So 2y is less than or equal to 16 minus x, divide everything by 2. So y is less than or equal to 8 minus 1/2 x. Okay, let's take a look at that now. So let's see. So x has to be greater than or equal to 3. So greater than or equal to 3. Y has to be greater than or equal to 2. Okay, well, that's interesting. So we have that. And then we have y is less than or equal to 8 minus 1/2 x. All right, so we have 2, 4, 6, 8. And minus 1/2 x. So it's going to be out here at 16. All right. Now we're looking for less than or equal to. Okay. So we have this, this, and this as our vertices. So what are these points? Well, out here I have 2 points that are along this line where x equals 3, right? So x equals 3, y equals 2. So those meet right here. So that is 3, 2. So we have the line where x equals 3 meets up with the line for y is less than or equal to 8 minus 1/2 x. So what that means for us, we have to go back once again and rearrange that, right? So if we had, so x plus 2y is less than or equal to 16. Just treat that like an equals right now. So x would be equal to 16 minus 2y. So x equals 3, x equals this. So we would say 3 equals 16 minus 2y. So 2y equals 13, because I'm adding 2y to both sides. Taking away 3, divide by 2, divide by 2. So y equals 13 halves. So we have 3, 2, 3 13 halves. And then the last point is out there where we have the line y equals 2 intersecting with the line y equals 8 minus 1/2 x. So 1/2 x equals 6, right? Because these are equal to each other. We substitute 2 in right here. So 1/2 x equals 6. Divide by fraction, you multiply by the reciprocal. So x equals 12. So we have 12, 2. Okay. All right. So we have our 3 vertices, and let's see, 4x plus 8y. All right. So 4x plus 8y. So we have 3, 2, 12, 2, and 3 13 halves. All right, so we're putting that into 4x plus 8y. So 4 times 3 plus 8 times 2, 4 times 12 plus 8 times 2, and we have 4 times 3 plus 8 times 13 halves. All right, so 12 plus 16, 28. 48 plus 16, Nintendo 64, Yahtzee right there. And then here we have 12 plus, oh, what's that? 2 goes into 2 once, goes into 8 4 times. 4 times 13. If you guys play any kind of card games, right, we have 4 suits, 13 cards per suit in a card deck, so that's 52 and 12, Nintendo 64. All right. Oh, that's interesting. Look at that. So we're looking for max and min. So the min's easy, right? Our min occurs 3, 2. Now the max is a little bit harder because we have 3 13/2 and the 12 2. So what does it mean for our max? Well, what that means is the slope of our objective function, right? So we have this 3 13/2 and we have this 12 2. So what that means is every single point between 3 and 12, every single XY pair right here is on the line of the graph of our objective function. All right. So what that means for us is that we have a max not at 2 points. All right, because that's what we're tempted to think at first. So it doesn't mean that we have a max at 2 places, right? It means that we have a max value of 64 at every single point between 3 and 12. Right, so we have a max on y equals -1/2 x plus 8 for every value of x between 3 and 12. That's what it means right there. All right, so we have that minimum of 3, 2, and we have our max of 64 at every single one of these points when x is between 3 and 12. That's what it means. Okay, so one more problem right here in this. So we have a guided practice problem. Not bad. Management. According to the manager of Pizza Shop, productivity and worker hours of workers is related to their positions. 1 worker hour is the amount of work done by an average employee in 1 hour. For the next 8-hour shift, she'll need 2 shift leaders, at least 2 associates, and at least 10 total workers. So at least, right, is that less than or equal to or greater than or equal to? Right, so we're saying at least means she can't have any less, but she can certainly have more. So at least is going to be greater than or equal to. Right there, same thing here. At least 10 total workers, so greater than or equal to. Just need to schedule at least 120 worker hours to meet customer demand. Oof. Assuming that each employee works an entire 8-hour shift, write an objective function and list the constraints that model the given situation. Sketch a graph of the region determined by the constraints to find how many workers should be scheduled to optimize labor costs. Well, let's set these equations up. So we're looking for, let's see, we're looking for a way to optimize labor costs. So that means our f of xy should be talking to this manager about money. So what's it going to cost for each person? Well, we know that we have to have 2 shift leaders, right? We know that we have to have at least 2 associates. So why don't we say that associates, that'll be x, employees, let's make those y. So associates, right, we have to have greater than or equal to 2. And if they make $7.50 an hour, then for an 8-hour shift, right, that's going to be $60 that she's going to have to pay for every associate. If we do $6.50 an hour for an 8-hour shift for every employee, that's going to be $52. So we have 2 shift leaders. So 8 hours at $9 an hour, 72. We double that. So $144. All right, so we're talking about labor costs right here. And we're talking about optimizing labor costs. Well, what do you think we're going to need right there? What do you think we're going to need for that? We don't want the max. We're going to look for the minimum value right here because we're talking about optimizing the cost of labor. So we want to make that as low as possible. We have to use our reasoning skills right there for that. So what do we need next? Well, if we have what it's going to cost them for an 8-hour shift, well, we know right now we have to have, we said at least 10 employees, right? So we don't know how many associates we need. We don't know how many employees we need. We do know that we have to have 2 shift leaders. And when we add all this together, we have to have at least 10. Now, the next thing we need is worker hours. Right? So we want to We sit there and maximize that stuff. So if we have 2 shift leaders and their productivity is 2 worker hours per hour, right, then that means over an 8-hour shift. So their worker hours will be 16 times 2, or 32 worker hours. All right. And let's see here. So she says we need to schedule at least 120 worker hours to meet customer demand during the shift. At least 120 worker hours. Okay, so at least 120. So the associate's productivity is 1.5 worker hours per hour. So 8 times 1.5. It's going to give us 12x. And then employees' worker hour productivity is 1 worker hour per hour. So that's going to be 8y. All right, so we have our objective function, and we have our 1, 2, 3 constraints. All right, so let's go ahead and let's sketch our graph and let's see how we can optimize these labor costs. All right, so we have x plus y plus 2 is greater than or equal to 10. So x plus y is greater than or equal to 8. So y is greater than or equal to 8 minus x. We had 12x plus 8y plus 32 is greater than or equal to 120. So we get rid of 32. 12x plus 8y is greater than or equal to 88. And let's see, so I'm going to take 12x over, then divide everything by 8. So y is going to be greater than or equal to 11 minus 1.5x. And then we had our x is greater than or equal to 2. All right, so now we have some things we can work with. So let's go ahead and let's try to graph those. So we have greater than or equal to 8 minus x. Okay, so we have 8 minus x. So that's going to come out over here, 8. So that's y is greater than or equal to 8 minus x. Then we want 11 minus 1.5x. So let's see what that's going to be. So with x, 11 divided by 3 halves, 11 divided by 7.3. So we have 11 minus so y is greater than or equal to 11 minus 1.5 x, and we have our what do we have here? We have x is greater than or equal to 2. All right, let's go ahead and let's shade. So we have greater than or equal to this, greater than or equal to that, and greater than or equal to this right here. So where in the world do we meet up? So we meet up in this area right over here. Right now, we don't want to shade into negative territory. I mean, obviously we could, but it doesn't make any sense because we're talking about dollars and cents. We're talking about people and hours. So we're not going to have negative values right there. So we have to use some common sense right here. So let's try to clean this thing up because we have ourselves, looks like okay, so that's a place, one vertex where x equals 2 meets up with the graph of y is greater than or equal to 11 minus 1/2 x. So that was 12x plus 8y. So if I take that and I rearrange that and solve x, so we have 12x plus 8y is greater than or equal to 120. And then we come down here and we have the place where 12x plus 8y is greater than or equal to 120 intersects with x plus y is greater than or equal to 10. All right. So let's see what we have here with these values. And then we also have, so do we have a third? 1, 2, and oh yes, we also have this third place right here. And that's easy enough because that is just an x-intercept. So the x-intercept part is easy. That's 8, 0. All right, now let's take a look at these two. So if x equals 2, I need to rearrange this one to solve for x. So minus 8y. And we still got 12x plus 8y minus 32, so that was 88. And we just divide by 12. So 2 is equal to 88 twelfths minus 8 twelfths y. So 8 twelfths y is equal to 88 twelfths. And then 2, if we have two whole units and it's broken up into a fraction that's made up of 12 pieces, so that's 88 minus 24. So that is 64 twelfths. So when we divide by a fraction, we keep, change, flip. So 64 over 8, so y is equal to 8 right there. So we have ourselves 8, 0, 2, 8. And what's our third? So we had where these two intersect. All right, so we have y equals 11 minus 1/2 x. Well, that's equal to 8 minus x. All right, so let's go ahead and bring these things together. So let me add the 1/2 x to both sides. Oh, come on. So 11 equals 8 plus 1/2 x. 1/2 x equals 3. Divide by 1/2. Multiply by the reciprocal. So x equals 6. All right. So when x is equal to 6, y is equal to 2. Okay. So now we know what we're dealing with because our f of xy, we've been waiting for this all class, right, to get to an ax plus by plus c. So now we actually have the ax plus by plus c because we had our 60x plus 52y plus 144. And now we have our 3 points. So we have our 2, 8, our 6, 2, our 8, 0. All right, so we put that in. So we have 60 times 2, 60 times 6, 60 times 8, plus 52 times 8, plus 52 times 2, plus 52 times 0, plus 144. So we're looking at costs, right? We want to optimize costs. That means we want the cheapest down here. So we have what? 120. So 416 plus 144. So we have 360 plus 104 plus 144. So 480 plus 144. All right. So you have 456, 660. So we have 680. We have 345, 608. And then we have 4580, 624. All right. So 608, that optimizes our labor cost, because the optimized labor cost means we want the minimum value, and that occurs if we have 6 associates and 2 employees. All right, guys, hope you enjoyed this video. We're going to talk about this. I'll also talk about 6.1 through 6.4 at today's Google Meet. So this is 6.5, linear optimization.